we got many results from this. And later on, we were discussing that if there are equipotential surfaces, for example, due to point charge, spherical surfaces are equipotential surfaces. Equipotential means potential is same at all points on the surface. So if there are equipotential surfaces, then we can find the direction of electric field by going from one surface to the another surface via the shortest route. And that direction of the shortest route, direction should be from higher potential towards the lower potential. It should be along the direction of fall. It should be along the direction of fall. So that's the shortest route, and this itself will be the direction of field. And that is correct. You know that. It is not just valid for this discussion where point charge was there. It is valid for any complex situation, any complex network of charge configuration. You just need to know the geometric shapes of various equipotential surfaces. So you go from one surface to the other surface via the shortest route, and that's how you keep on getting the direction of field. A very simple analogy, just to help you remember this, is look at any waterfall. Look at any waterfall. Waterfalls from higher to lower direction. Exactly this is the thing happening here. Potential fall is just like waterfall. So direction of waterfall gives you the direction of gravitational field. Direction of waterfall gives you the direction of gravitational field. Same type of thing you have to apply here. These are all parallel lines. All of these are parallel lines. So it will be 30 degree for everybody. And when we say line, this is an equipotential line. Everywhere 10 volt, 10 volt, 10 volt. 20 volt, 20 volt, 20 volt. Just like equipotential surface concept. This is 2D, XY basically. When we talk of point charge, it's a 3D situation. So equipotential surface is spherical surface. This is XY plane we are talking about. So in that plane there are several equipotential lines. 10 centimeter distance, 20 centimeter, 30 and 40. Now, what can you say about the magnitude and direction of electric field? Let's follow the rule. Potential fall. We can choose any two. It's all symmetric. Any two equipotential line we can choose. Let's choose these two. From one go to the other via the shortest possible distance. You know that the shortest possible distance between parallel lines is the perpendicular distance. Fall, okay. Fall, when I say, then I should go from higher to lower. So we are walking like this. That will be the shortest distance. So that direction is the direction of field. So we already know the direction of the field. How will we give the answer? 30 degree, 90, 60 degree, 120 degree. So we can say 120 degree in positive sense with respect to the x-axis. Now, talking about magnitude. So, theta I have chosen as, well, cos theta I have chosen as 1. When I choose this path, shortest path, it automatically means that I have chosen cos theta as 1. And I'm just interested in positive value for magnitude. Delta is final minus initial. Answer will automatically come out to be positive. How much is this distance, dr? This is 10. This is 30. So how much is that? This is 10, this is 30, so this is 60. 10 cos 60. But this 10 is centimeters. This is volt. Yes.
Sir, is it not 10 cos 30?
In this right angle triangle, you want this. This is 30, this is 60. This is 10, this is 60. So 10 cos 60. Cos 60 is half. (200 volt per meter) at 120-degree angle. Any questions? Let me know. Well, while they don't look circular, assume that they are circular. So these are three equipotential surfaces: 10 centimeter radius, 20 centimeter radius, 30 centimeter radius. The question is, what is the magnitude and direction of electric field? Magnitude and direction of electric field. So let's move from one point to the other point. Shortest distance will be along the radial direction only. So clearly, direction will be this, radial. That will be true if you consider any other point. Radial everywhere. Regarding the magnitude, now how do you find the magnitude? Again the same thing. When we are walking in this direction, cos theta is anyway 1. So minus dV by dr, that is E. Now this problem has got a trap. Previous problem had same dV, 20 minus 10, 30 minus 20, 40 minus 30. dV was change in potential was same, 10, 10, 10. If you traveled the same amount, dV was same. So it was an easy question. Now here, if I take these two, then dV is 60 minus 30. But if I go from here to here, it is 30 minus 20. So if I write like this, it will be a mistake, isn't it? So if field is not constant, this is what you will find. If field is not constant, this is what you will find. You travel the same distance and fall in potential is different. 60 minus 30, 30 minus 20. You travel the same distance, and if you are finding that change in potential is not same, you are traveling the same distance via the shortest route, then it means that it is not constant field, and this is not the way to do it then. This is wrong. Then how do we do it? We try to see some pattern. When R is 10, potential is 60. R is 20, potential is 30. R is 30, potential is 20. It shows that V into R is constant. Right? And we know that constant also. That constant is 600 volt centimeter or 6 volt meter. Now, I just need to differentiate. In place of V, I am going to put 6 by R. 6 comes out, derivative minus 1 by R square. So 6 by R square. So one has to be careful in such problems. Putting dV and dr like this would work only in those questions where field is uniform, constant field. How would the field lines look like that? Constant field. Equally spaced everywhere throughout the plane. If that is not the case, there would be some dependence on x, y, z, etc. or r theta. Any questions? Let me know.
So can you explain 6 by R step?
This one? V into R is 6. So V is equal to 6 by R. That's what I put here. Anything else, let me know. Now, we got the formula for field due to a ring, and we also got the formula for potential. When we got the formula for field, that time we had not, I think, discussed potential. You must have seen how easy it was to find potential in comparison to finding field. Can't we get the formula for field from potential at this stage? If you see your notes, you should be able to find the result that we got for potential. What was it? Let me write. It was this, I suppose. Now, we use some argument of symmetry and say that field must be along the axis. Using the argument of symmetry, field should only be in this direction. And it should be as simple as this. See if it is the same result that we got via integration, taking components. Note that we are treating x as a variable here. Any questions? Let me know.
Sir, is A is a constant?
If there was any question, you need to repeat it.
Sir, is A is a constant?
A is a radius. Radius is constant. Dipole. From chemistry, you know the meaning of dipole. In magnetism, you have everything dipole. So, what we are discussing now, that will resonate with magnetism also. We can make dipole in electricity like this, minus Q and plus Q, separated by some distance. We define the dipole moment as a vector where vector D has direction from negative to positive. Vector D is from negative to positive. We are interested in knowing field and potential at a point due to the dipole. And what we will do is that we will first find potential, then we will differentiate and find field. That makes sense, isn't it? Join these two. This is also called the axis of the dipole. That point can be anywhere, but it should be far away. Far away with respect to what? This distance. So normally we would say that D is small. That's the approximation we are making. If D is not small, don't use the result which we are going to obtain. This distance we will take from the center. Let it be, say, D or R. Now D, okay, D I will take as this, so let it be R. D by 2, D by 2. Finding potential should be easy. I need this distance, I need this distance. So when we say a point, we need R, fine, R is given, we need theta also. Either we deal in XY system or we deal in R theta system. Let's deal in R theta system. I need this distance. I need this distance also. Dropping a perpendicular. Extending. Dropping a perpendicular. This is D by 2. D by 2 cos theta, D by 2 sin theta. This is D by 2 cos theta. So from here to here, it will be R minus D by 2 cos theta. From here to here. But if we are saying that distance is large in comparison to D, then from here to here is same as from here to here. From here to here is same as from here to here. Of course, approximately. Likewise, we know this distance, we need this distance. That should be same as this distance. Again, approximately. And this distance is, this is D by 2. This is theta, so this is theta. This is D by 2 cos theta. From here to here it is R, and then D by 2 cos theta. Potential due to plus Q. This is approximate, right? Because this itself is approximate. Potential due to minus Q. Again, it is approximate. Total potential. Just add let's see if we can do further approximation. to make it look more friendly, easy. We know that R is much larger than D. Well, that means R square will be huge in comparison to D square. I think we can neglect this with respect to this. Now that means we have this, of course, approximately. But QD is called P, dipole moment. So PD cos theta, just go ahead, by R square.
So shouldn't K also come?
K should come. K. That's our final result. Any questions? Let me know. Note that it has got R square in the denominator. When you look at an isolated point charge, R square doesn't come in the bottom. R comes. For potential. So this standard result is in R theta format. Now we have got a problem. Our intention is to find field from this formula, potential formula. But what we have discussed regarding the relationship between field and potential, in that we have used Cartesian. This is Cartesian. And likewise, others also. Cartesian is what we have discussed. And if I don't, yes, go ahead.
Sir, in the previous board, sir, why have we assumed that R has to be much greater than D?
That's the case most of the times. That's the case most of the times. So that's why we are doing it. If it is not so, then we can't make approximations, but we can solve any problem using this method. Whether you have got 2 charges or you have got 5 charges, you want potential at a point. You will just take one charge at a time, add all the potentials. So why are we doing it for large R? Because that's what happens most of the times. R is very large in comparison to D, normally. Yes, anything else? Yes, go ahead.
Sir, in the last case, it will be Kp cos theta by R square.
Kp, yes, D has already been merged with Q. Good that you pointed that out, because that was the final result. Kp cos theta by R square. Yes, anything else? Right. Now, suppose we are talking about just XY plane, then I don't need EZ. But still, these two results are valid for Cartesian system. And we have gone for R theta system. So how do we solve this problem? There are many systems for your information. In 3D, if we speak, we have Cartesian system, we have cylindrical coordinate system, we have spherical coordinate system. Cartesian, cylindrical and spherical. you don't need to get into those things too much, but r theta you need to know. 2 dimensions, that is. 3 dimensions, cylindrical and spherical, they become complicated. 2 dimensions r theta system if you want to use. And we do need that. Circular motion analysis was using r theta system. So if you are using r theta system, then r is distance, so dimensionally nothing will be wrong. If I write this, dimensionally nothing will be wrong. But if I write theta component is a perpendicular component. R theta system means Ex, Ey will have these directions, right, respectively. R theta system means Er, E theta. R and theta directions are perpendicular directions. They are radial and tangential directions, right? But the problem is that if we write this, then dimensionally it is not correct. You can check that. Volt per meter you want, right? So you will have to remember this, that theta component is given by minus 1 by r dou v by dou r. Now you can see that no problem with dimensions. Any questions? If you have, then let me know.
Sir, you did not change this dou theta.
Did not change? No, no, because the theta is like dimensionless type of thing, right? So no problem with that. Volt per meter, volt per meter. Now, A is constant, B is constant. Partial differentiation, right? So cos theta is also constant. Done. That's ER. Let's find E theta now. P constant, K constant, partial derivatives, so R square also constant. Then dou theta of cos theta. That means Kp sin theta by R cube. Any problem with ER and E theta? If you have, then let me know. So in vector form, vector E is ER unit vector along radial direction cap plus E theta unit vector along tangential direction or theta direction Any questions? Let me know.
So what is E here?
Unit vector. ER whole thing is a unit vector along R direction. When we want to represent unit vector along theta direction, instead of using theta cap, we use E theta cap. That's it. Now, this question is your assignment question. We stop now.